So the best for these recordings might be that when we upload the Basecamp. Basecamp, I'm not sure for the limit.
Yeah.
We'll see.
Oh. Okay. Yeah, okay. As I said, a short overview about our ecosystem, thoughts, lessons learned, maybe also a little bit. And you need to know, Pigon GPU is now around 15 years old, and this was our first code. It was started to be written from scratch in CUDA. So we had a very, very big advantage. We do not have started with any legacy data structures or something like that. Our first version was really focused on CUDA. You need to know in the past, NVIDIA GPU had something like 2.6 gigabyte of main memory, and if you have enabled ECC, then it was only a little bit over 2 gigabyte. So we started also with a lot of thinking that we have not enough memory always to represent all our physics. So we decided very in the beginning to do a lot of stuff compile time, in hopes that we do not need to carry around a lot of variables and data to the GPU, because there was no space to store anything. So Michael was training us that is made a template programming, and every one of us was young, and it was really fancy. It was C++98. It was a nightmare compared to how you program now in modern C++, all this stuff. But the first thing we learned from him was that you should try to separate orthogonal concepts. And you should identify this orthogonal concept as soon as possible, because this is something you need for meta template programming, that you can have a policy-based design. That you can, for example, if you look into the STL and you have a standard vector, what is following a concept, it is a concept of containers, and it is describing what the container needs to carry on, how it needs to behave, and you have, for example, the allocator policies that you can say, okay, by default, there's an embedded summer that is using new in the backend or something like that, but you can always provide for any kind of standard vector your own allocator. So it is a policy you can swap out. This must follow a defined concept, but you need to identify that allocation of a container and using a container are two different things, or the representation of the containers are two different things. And this is also what we then later on reflect strongly in our ecosystem. So mostly all projects we had started somewhere in Pigon GPU as prototype, as part somewhere in Pigon GPU. But at some moment we realized, oh, we are now well trained in describing what we like to do. And it is orthogonal to what we are normally doing in Pigon GPU, or we have a small library in Pigon GPU. It's particle mesh acceleration, which is handling all this distributed main memory, API communications, and it's also giving the interface to Alpaca, or in our case, Coupler, which is a little bit CUDA-like. So this is also something for other projects. If you see something where you say, oh, this is not really specific only to my application, this could help other in the community too. Start as soon as possible to move this stuff out of your project, make it independent, and hopefully have the capacity to make it also nice. So therefore, as I said before, yesterday I heard about the hashmap, and my brain was jumping, because this could be really useful for us maybe too, but I don't like to invest the time to implement the hashmap. And why should I? Because they did already a good job, and why not adapting stuff or extending stuff from them that is then maybe compatible with Alpaca in our case, or if we have an interesting project which is currently bound to Alpaca, why not maybe make it again independent of Alpaca? Because maybe the key concepts can be really easily swapped out, that Alpaca is only maybe in an acceleration strategy or policy, and you can use then also easily native implementations, CUDA, LIP, or something like that. So this is something I'd like to make you aware. This is good practice, helping the community, and helping also you as maintainer of the software, because it is much easier to write unit tests, to create a unit test pipeline for a well-defined project. It is only communication, it is only maybe distributed memory or something, or distributed containers, or it is only allocation, it is only abstracting away the hardware, what Alpaca is doing. So if you find something like that, separate it. And separation means also what we talked the first day, that we said it's not my code, it's not your code. So a lot of our software is also, so all our entry point to all our ecosystems is always GitHub, because we do not like, we do not like to put everything on our local HCDR GitLab we are using, because it is for many users or in the community much easier to have a GitHub account, and maybe GitLab is, so the local GitLab infrastructure is more hard to use, and maybe already and maybe because of laziness or no time, and barrier the user needs to go over to get access to the code or to contribute. So therefore, GitHub, nearly each developer in the world has a GitHub account, so he can interact with them. So yeah, a lot of stuff started in Pick on GPU. So we have Pick on GPU. This is a fully compiled Python code. It's sometimes not hard to use, but we have still a lot of abstractions in. I like to talk a little bit over. I don't like to show how we use Pick on GPU. But what I like to make you aware is, for example, that we love abstractions. You have maybe realized it already, because we abstract everything away. We have an abstraction called batch system, because in the past we had more batch systems than currently. Currently, nearly everyone is using Slurm, and Summit, for example, is using LSF from IBM. I think this is the right name. And they are different to use, but we do not like to say our users, okay, you need to write your LSF file, you need to write this file. So we have a template we provide mostly for the user, which is describing also the node. So which architecture is this? Or most likely we define in queues, because we are working very often on heterogeneous HPC systems. They have a CPU-only partition, a GPU partition. So we abstract it away. We can describe in a very easy batch way how the system looks like, and then the user only need to say, okay, I like to run 1,000 MPI ranks, and we define what is the best mapping of an MPI rank to node or so, and we can calculate how much nodes you need, and then generate a global batch script, what is can be understood by the batch system. And even if you have a Slurm on one system, the Slurm on another system is still different, even if it is Slurm, because it started with how I need to pin my MPI process to the right course, that they are near to the GPU, because if you do not pin your processes correctly, you have latency fluctuations in case the operating system is moving your process to the wrong NUMA domain, or wrong processor maybe, because if you have a dual socket, this is also very important.
Can you briefly show an example how you describe a machine like this?
Yeah, for sure. Let's go to, yeah, let's go to Frontier. Okay, we started with the name Frontier. So in Frontier, there's luckily only one queue. So what we always provide for each system is an example profile. So this is something really basic. We say each user, please do not add any module file in your BAPSC, because it is fine as long as you work only with one project, always with the same code. But as soon as you use two codes, OPX maybe and GPU in our case, it is a nightmare because the modules are maybe different. Anytime, start with your session, load a file which is loading in the right module. So we provide the user with such a file. So for pick on GPUs, it's now special for pick on GPU. We say, okay, there's a project that you need to fill in your project ID. You can define your default editor because we're providing some helper tools. If you say, okay, I like to create a new simulation input, and we have separated the simulation input in thousands of files. We have a small helper tool, which is where you can say, okay, I like to configure the memory. So this then out of the source code copying the file into your parameter set. It's a separate folder, and then open your sound editor. It's only for helping. So
this oversubscription, there was nodes oversubscription. Why this is used?
node
Oversubscribe the nodes allocated by N per thousand.
okay. This is something what I added as in special for Frontier and for Summit. That here the user can be defined that this very can be accessing in your environment, where we say, okay, 2 per mil, you allocate always 2 per mil more nodes than you really need. So if you need 1,000 nodes, we will allocate 1,002 nodes for you. And later on, you start your simulation. You say, okay, I like to run it on 1,000 MPI ranks. And we will then allocate 1,002 because maybe some nodes are broken. So we do a health check in the beginning if everything is working. If we detect during the health check a node which is not healed anymore, this sometimes happens. It also depends on the quality of your facility. Then we write a negative list, disable it from your batch system, and then we start the right job. Pick on GPU, for example, hopefully only on healed nodes. It could be there and then dead again, but then we are very unlucky. But this is the current suggested way from Oak Ridge how you should do your failure handling for broken nodes. So even then, in Frontier, the wall time and all is limited, I think, to 6 or 12 hours. Because I think the possibility that your job is crashing up after 6 hours is 50% or something like that. Because one of the nodes, if you use full system, will definitely die in that time, currently, because it is a little bit more unstable than it should be. But this can be happened on any system. It's not specific to this facility. So it is only and something what we added. That,
you do then your own node list and you start with.
Yeah, we take the node list from the batch system and remove the broken nodes. So in Slurm you can say the negative list, which nodes you don't like to have. And the batch system is providing us with a long list of nodes, and we removing some of them if they are broken, and if all are healed, we removing still some of them because we don't need to have all of them and then spawn our MPI context. But this is only really important for if you run full Titan or half of the Titan, because then it will become important, because you wait maybe 2 or 3 days or a week until your job is starting, and then the system was free and your job is starting and crashing instantly. Is not really good then to wait another week. But yes, it's in that case easy to handle this, to find the starting failure. That's you can say. But if it is crashing during simulation, yeah, hopefully you have written checkpoints. Yeah, then this file is only containing the modules for this system, which are working very well with Big on GPU. We have most likely tested. Sometimes also some environment variables you need to set to utilize maybe some features, like in that case MPI. Here you need to pass beside our project using CMake, but on this system you need to give your CMake compiler some more flags, so we did it for the user, that the user do not need to know about it, load OPD and all the stuff. defining here also which architecture it is. On front we use HIP as accelerator, and then the architecture is GFX 900A. And for example, if we later on going to a BISC-V, we most likely will use a serial accelerator of Alpaca or maybe OpenP2 accelerator, and then we can write whatever this RISC name was. Tivoli substitute synthesizer. Okay. Then the user has loaded the right modules, and then the system description is exactly your batch file, but with a lot of placeholders. So everyone who ever wrote a submission file knows exactly this. This is Slurm. It really depends what you need. For example, on front here, you need to say bind my process to the closest GPU. You say how many GPUs, and pick on GPU. We have a one-to-one relation between MPI process and a GPU. So one MPI process is only using one GPU, not more than one. We can explain it in that case to the batch system. Then we have, this is now special for our TVG is template batch generator, and this TVG is written in bash. It is really, really ugly string substitution. It is no fun. It's no fun to debug. But at the time where we started, also no cluster had Python on it. So even now, it's very often also a nightmare to have Python, but it's easier. So we decided in the past we use bash, because a bash script can be executed everywhere. We do not need to poke the maintainers or the vendor that the Python is available and everything is working. So therefore, our infrastructure for the user is written in bash. You have some variables which are get passed to the user. So here, for example, you have the definition how much main memory you have per GPU. So we hard coded it here because the GPU is known. We say how many devices we have per node. So take care. We should also maybe also in the project more speak about accelerator devices instead of always saying GPU, because an accelerator device could be also a CPU or the RISC-V accelerator type. So GPU is already branding everyone in his brain to oh, we use CUDA, or oh, we use AMD GPU. No, there's more. There could be an FPGA accelerator or something else, or you accelerate the code on the CPU. It's a simple device. So GPU is branding everything a little bit. We have it still in our code base a lot, but we try to avoid it, and maybe it's a good practice at all. Yes, then you say how much cores you are allowed to use per rank later on. So on Frontier, there's a limitation. If you use one GPU, that you should use 7 cores, because one core per package you are not allowed. If you use it, then the job is crashing, because it's dedicated core for the operating system. You can't pin your application on that. This is very specific. Yeah, then we calculate here how many MPI tasks we can spawn with the knowledge of how many devices we have on a node. Yeah, we generate for ourselves everything we need to describe the job. How many nodes we need. This how many tasks we need is coming later on from the user. This is a template. This is fixed for the queue, for example. But the user is then manipulating a config file for each simulation, where he's then really saying, okay, I like to run on 1,000 devices, I like to run on 10 devices, and then 1,000 devices, we will calculate how many nodes we need, and then generate out of this knowledge a normal batch file, same as you've written it by hand, and apply it to the batch system if you like. So all our tools are written that they are transparent, so it's all helper tools. You can always write a batch file by hand. And if we generate something, we put it into the directory of the run, also that you know what config file you used at start time, what template have you used, and also what is the result after all this substitution and everything, so that you have always the full control, that we try to avoid any hidden stuff that we do magic and the user do not realize that something happened. if we compile our application, we have also a wrapper. It's called pig build, where you can really easy say pig build minus b serials, and it's compiled for serial accelerator. And this helper is only extending the CMake string a little bit, but we show the CMake string to the user and say, hey user, you can also execute this native CMake string, but you should not, because it becomes very, very long.
So in this case, now this file has not to be modified by the user involved. This is just read for your bash script that is generating then a submit script, and this in the end the user can then or has to modify, for example, setting the time, setting the number of processes.
This is not required at any point to modify if the module is not changed and so on, and this is something we most likely produce once, and then it hopefully is possible to use forever. It is mostly not the case, because also a big facility changed how you should use Slurm at the point. And I also talked about this config file and the user. I will go to a Pick on GPU example. We go to the Kelvin Hollenholz, what he showed today in the OpenPMD presentation. And this is a config file where we have special names where we say, okay, what is the wall time? Sometimes the wall time format is also different on the batch systems. We can, in the template file, transform it to the right format, whatever the batch system file requires. The user can then say the distribution, so the main distribution, in this case, 1 GPU, but he can also say, okay, in Y direction, I like to have 1,000 GPUs or 2, and if these are only helper variables, you can write also everything on one line. And at the end, the only requirement for our template batch generator is that you have TVG tasks at the end, and you say how many tasks you have. Here I only multiply the values above. And we also require then in the template, but it's not coming from template batch generator, because the template batch generator is quite generic. You could use it for any program. We have it currently only for Pick on GPU, but you can use it for any application to abstract away your batch system. And these are parameters then which are going to Pick on GPU. So it's defined by Pick on GPU that D means the distribution of devices, 10 by 10 by 10, for example, for 1,000, the grid size in each dimension, and the steps. And these are with a exclamation mark, obviously placeholder, which are then later on substituted. So they are defined above and they are substituted. One fun fact about this, since this is template substitution, you can use a placeholder before you have to find the placeholder. You can define it later on. It's a little bit ugly if you think about this. This is pure bash.
But I saw that .tbg and this I would not understood.
Oh yeah, that's a little bit special. That's this template batch generator has a special behavior. You write this, and there are two timelines when you execute it. At the end, there's a file coming out. You see it, there's a Speng for bash above. That this will be later on executed from the batch system. You will give it really this S-batch, for example, to a Slurm bash system. And everything what has a dot in begin will be evaluated at the time where the user is calling TVG, at the time where the templates are substituted and you generate the batch file. And everything what is not with the dot starting, the definition, this is part which is executed later on in the end script, but is really then used by the batch system. It's a normal script where you say, okay, create my output folder and now run, show it, now run my application with srun, for example, on the system. So we have two timelines when this script is executed twice, once during...
Like in Slurm, you have hash as batch, you have now dot as beginning.
In Slurm, the hash commands, this will be substituted at the moment where this variable will be used. For example, here you see we define the queue is a batch queue, and here we use it. Here's an example. We use the variable before we define the variable to define the queue where it is running.
So at the end, you don't get the batch file.
At the end, you get the batch file, and we what?
You don't see it.
You can you can see it. You can directly say to the batch generator, submit it directly to Slurm. But in any case, it will be stored on the on your file system, and you have later on access, and you can review it. And then all this dot something will be removed. So this you can think of the resulting batch file. Everything with this exclamation mark will be substituted. You will have the result from the evaluation at the moment where you call the program, and all dot something variables will be removed. You don't have it in a final script you are executing. It's a complicated thinking, and it's generic, as I said, but here this template is not written really generic. It is focused on pick on GPU. Therefore, you have also hard coded here call pick on GPU, and with a lot of placeholders, where's pick on GPU, which node should be excluded. This is something we evaluated before. So at all we do here the heal we do the heals test here with CUDA mem test. So it is filling your full GPU memory with patterns, byte patterns, is reading it back and checking if there are bit flips or something other, or maybe the application is crashing because the GPU is not available. It's also very often the case that you get a node. Normally there are hardware of GPUs in, but if you then ask your CUDA or something like that, give me GPU 0, nothing happens. The node is dying or something like that. This is something where we try to detect it.
Quite bright. So now you can have a job name as variable, otherwise you cannot.
Yeah, our job name, for example, we also can derive out of a little bit bash magic. So I think job name, TBG job name, we derive from the destination folder. TBG, you say then execute my application in this folder, then all binaries get copied to this folder, so that you have your own vault. You can change your binary, the original binary already, and from that we derive the name. But you can do everything what you like, because here you can apply any bash function. So even you could use your environment variables, and here, for example, in the profile we have variable myMail. This is meaning if myMail is existing, then use this as value, except if it is not existing, this is the default value you should use. And you can, at the moment where you submit your job, read also through your environment what variables are available, and somehow formulate it into the definition, how many nodes you like to use, or in the job name or whatever. But this job name is only something that you have a better view as human on the queue.
So what do you type when you submit? TBG something.
Yeah. So let's go to the documentation. I think we have an example there. Here we have an example. You say TBG, you say -s is submit, so it is really then giving the final solve template to SBatch. This is for Slurm the tool. So if you load our profiles, this SBatch is already configured because it will not change on the system. You can only say -s submit it directly. If you skip the -s, for example, it is then simply writing the file only to disk. You say there's a config file, you say there's a template, and normally, since we already also defined what is the default template for a queue, and you have loaded this profile before, you also only need to say -t that there is a template, use the default template, but you can always say, okay, no, use this template because I'm currently the developer and changing the template or so. And then you say where the job should be started. And then TPG is doing all this copy action and everything. But what is really copied is also then defined in this config file. So the config file itself is again a batch script that will be executed at the time where you call TPG. So if I write now this on my command line, and that in this moment, the TPG file will be executed as bash file. And the file you're getting out, you can also then go to the terminal and say sbatch and the file, and then it's submitted. But this is only abstracting away the batch system that you have a look and feel on any system what is equal. So even if you go to our development system where we do not have a bash system, I'm mixing bash and batch. You do not have a batch system on, so you need to execute everything in a bash. We have a template which is saying, okay, the bash is my batch system. And you say TPG, do it, and it will instantly generate also your template, solve everything, and execute your application directly on your terminal. So the workflow is always for Pick on GPU equal if you have an HPC system, if you run it on your laptop or wherever. So therefore I said we abstract away mostly everything.
TPG could be like run command.
It's like a run command, yeah. I'm very bad in naming, and for unknown reason we gives this name, but yeah, we haven't changed it, but yeah, it is now accepted by all users. That's TPG. It's in the documentation. Yeah. Should I say more to Pick on GPU or skip that? Or is there something interesting?
Yeah, so it's just one quick question. So the setup is it just focus on devices. So I'm thinking, how do you do it? How would you would focus about this setup for like multi-core, just CPU? Because it looks like it's just devices, so GPUs.
Oh, if you like to use CPU or GPU, it depends what you define, for example, in the profile, or what you say on the terminal.
Then a device would be a core, right? Would be
it's
the CPU in this case.
Right, yeah. So as I said before, we always load the profile. This is on our development system. I'm loading now all the modules. We have Spark on the system, maintain everything with Spark, that we have all these hierarchies, that CUDA NPI is correct built. So there's a lot of Spark loads behind this command. Let's go to I have now somewhere my source code laying around of Pick on GPU, and now what I'm saying, okay, Pick create as a helper that I like now to create a new input set for a new simulation, and most likely if you will set up your experiment, your virtual experiment, you most likely clone one of our several examples, and you then change maybe the time steps, the size of the cell, whatever you need to activate new algorithms and so on. But most likely you start with something pre-existing, and then you shrink it down or increase it in complexity. So I start saying now, okay, create me a parameter set. I say there's my source code. I use the example laser wave field, for example, put it in the folder laser wave field FSC. So then I need to go into this parameter set, and if I call now our compiled helper pick build, I loaded my profile already. It will automatically know, okay, we have a GPU, and NVIDIA GPU is set. My profile is saying that there's a NVIDIA GPU in this system. That's a little bit a lie, because we have also two AMD GPUs in the system, but my profile is saying it. So it is automatically now knowing, okay, we need to say Alpaca, that we have CUDA accelerator, this is enabled. There's a special Alpaca command that we use only one accelerator, and which architecture it is 80 for AMD. There's a naming behind. For CPU, you can say something like native. It's then MArch native, where you really compile for the instruction set your CPU has, or for a RISC-V, you would say it is in the name of the RISC-V. So, but this would now generate a pick on GPU for the NVIDIA GPU of, it's a A30, it's an Ampere GPU, 80. But I can also now pick, so this is in my environment stored what GPU I like to have, but I can always override what I like to do. And I can now also say, okay, it's.
Oh, you can just control the
Yeah, just scroll up, just,
you cannot move it.
I cannot move it.
just press enter and the screen will go up.
I don't know,
Okay.
maybe.
I can now also say, oh, I need to remove my build folder maybe, because CUDA was already pre-compiled. So I can now easily say, build it for a serial accelerator for Alpaca. And now, as I said, we try to be transparent. We really say what is the CMake command for everything. We are now saying, okay, it's an Alpaca accelerator, it's serial execution. The naming out is really bad. We change it in the next version that it becomes human readable what we use. And it's not for CPU. We do not use asynchronous streams. So if you know CUDA, for example, you can have synchronous executions or blocking streams, and you can have asynchronous streams. For CPU, we don't use asynchronous streams, because in Alpaca we would, or how pick on GPU is also implemented, we would waste one core which is calling all the time if an actually an event is ready. It's an optimization, but now it would create a serial binary. Maybe I shouldn't stop it. This took now two minutes or something like that. And you also see we do everything with CMake. We have optional dependencies for pick on GPU, like OpenPMD. It is enabled, it was found by default. You can also force disable it if you like. Isaac was not found, the dependencies are not here. And PNG writer that you can easily create some PNGs. Yeah, then you need to wait, depending on your setup and on your system and on your file system, 2 minutes to 30 minutes. Then your binary is compiled, and then you can submit it to your system.
Okay, so once it calls that CPU backend, that means that automatically right now it's the CPU targeting.
Yeah, that's exactly. This is
all the devices that you have in the X, Y, and they're not cores. Is that what happening?
Alpaca is seeing one CPU node as one device. We haven't implemented for now in Alpaca that you see each NUMA domain as independent device. It would be possible, it's only a little bit work. We haven't done it. So in the CPU case, you see one node. If you have two socket system, you see both CPUs as one device. But I said now it should be executed serial. This means it will be executed really on one core only.
Yeah.
So
that's what I'm wondering. So how do you do it with multi-core? How do you handle the multi-core? Because one node is one device, right?
Exactly. In that case, I would compile it for example, for the OpenMP2 backend, and then the all cores of the node will be utilized. Yeah, and then now you could call So all our tools are always supporting help. You will get a big list of options you can apply to run it. And that's now. So now the auto completion is not working on the system.
But why the submission script is not in the template already?
This is my laziness. My profile is really my profile I loaded is really dirty. Therefore, not everything is well configured. I haven't used what we have in the code base because I'm developing too much, and sometimes I skip some steps and execute the binary mostly natively without TPG or something like that. Normally, it is much easier to execute it. Okay, TPG I can't show, but I can show Pickon GPU. Let's say, okay, oh, I'm serial. I have 64. I have 60. Oh no, since I'm serial, I have now 64 cores. I can spawn an MPI process per core. I now say, okay, use 64 devices. Maybe I should distribute it a little bit more even. Okay, I can arbitrary bit size. Let's say 111. It's a good bit, and say 100 time steps, and let us add periodic boundaries. This is what I know out of my head. Oh, thanks. I now, since I do not use currently TPG exactly, I have now the problem that I need now to know how to use MPI correctly. Luckily, in that case, it's quite easy.
Yeah, so that's it. You have to put subscribe.
And let's go to sleep. So now with this tiny example, I started one by one cell. This is not possible. We have some constraints in Pickon GPU. You need we have blocks. It's called supercells. You need 3 in each direction at least. So it is now auto adjusting your domain to fit our constraints. So at the end, I was now executing 48 cells by 92 by 24. And yeah, it was executing something, not simulating something useful, but it was running on CPU on N cores now. Okay. So this is how we work with Pickon GPU. And if you look in the configuration what I was running, as I said, we use always source code to describe something. So we changed the default ending. Everything is C++ code, but we called our files for set up a virtual experiment param that the users a little bit freeing his head from, oh, I need now to touch code also. It's quite easy. For example, dimension. If I like to run the simulation in 2D, I can easily change this define or write it here directly. It's only some more interaction. Say run it in 2D, compile it again, then I can run everything in 2D. And the same is for the initialization of particles, for example, species initialization. We have a pipeline which is describing what do I need to do to start the simulation. Ignore this stuff above because it's a case I currently compiled only for this stuff. And it is saying, okay, create me a density profile, what is Gaussian distribution of particles. In our case, it's always bidirection. Within each cell deposits the particles randomly. How many particles you need per cell is defined somewhere else in a file. We have a we predefined, if we predefined ions somewhere else, the ions will be placed, then we say, okay, the ions should be pre-ionized, and we say, okay, set our number of bound electrons for this species to a special value. It's what set bound electrons is a simple C++ functor is also defined in another file. And this is how pick on GPU works. So you need to write, this is all C++ code. So it's not that you need to write a function here. You need to deliver a lot of functor signatures which are having a definition of the behavior, what you are doing. So, and this is a little bit hard for users to learn. So we are also on the way to make it a little bit more user-friendly, but this takes time. But it's also only an implementation.
You could now, without recompilation, run with a different grid.
No, a different grid. This is possible.
Yeah.
No, different grid.
My question is, what is the reasoning in what is a compile time parameter and what is a runtime parameter?
For example, so different grid in number of cells, this is possible. But changing the size of each cell will require a recompile. And the reason for that is that pick on GPU, you configure everything in SI units, but pick on GPU is then applying an own normalization that you not run any, you are still in some kind of SI unit system, but with some normalization factors in to fit into the 32-bit variables very well with all the properties we have. And for example, the cell size is used for our unit system to define what is the typical length in the simulation. The time step is used for normalization of the unit time, for example. At the end, our unit time, for example, or speed of light in the simulation is 1. And everywhere in the code where you write speed of light squared, there's a code will see at compile time 1 squared. Hopefully the compiler is removing all this stuff, because why should I square 1 or something? A good test for pick on GPU would be to change the normalization to say speed of light is 2, because then we see if you miss somewhere a seed square. We haven't done it. So our normalization at the end is the reason why we have a lot of compile time stuff in. We need to normalize all the units and all values, and so we calculate everything then in 32-bit, write it then in 32-bit to OpenPMD in our internal representation, but this would be absolutely useless for the user, because you need to know the conversion factors, and then OpenPMD is coming and saying, okay, provide me the unit SI, then I know how to transfer it into SI units, and the user can really do analysis with that.
And do you have an estimate how much more performance it buys you to the normalization, for example, Python?
Oh!
Do you have an estimate on whether it's really paying off, or is more for the fun of it?
This is system specific. The first what you have, so 2-bit compared to 64-bit, half the memory footprint in the main memory. This means for the physicist, I can put twice as much particle in my GPU. That's amazing. This means.
No, but my question is more that you could also do the normalization at runtime rather than compile time. So you aim probably to save on some computations during runtime by doing all of it at compile time. And whether you have an estimate whether this pays off, and if, by how much?
There are a little bit of hope sometimes also in, because parts of your equations are always compile time known. So hopefully the compiler is throwing away, for example, all C square and so on. This means also hopefully you do not have the register usage for this single value. So we save one register everywhere you use a speed of light in our equation. This is amazing, one register. So we try to use as less registers as possible on the GPU. So each register is counting. So this will reduce, hopefully, so I cannot really say that it is, the footprint. The other stuff is much easier to provide a compile time value into your code than a runtime value, because this means I need to give to each of my kernels somehow the access to any conversion factor of the SI unit, because maybe you need to convert on the GPU. So it's in compile time, it's quite easy. I write my name of the conversion factor into the code, and then it's there at one time. I can use a global variable also on a GPU. On Cycles, it's currently not possible. It's only an extension from Intel, which is not in the standard at the moment. And yeah, that's one of the reasons. And yeah, in the past it was really motivated by the memory footprint and simpler interfaces that you do not need to pass thousands of variables into your kernel. Yeah. Questions on GPU?
Yeah, so on the configuration file, so where exactly in the configuration file where you select the different backends for the visualization part?
For what?
For the visualization, to see the output of the sim. So you just did the simulation, right?
Yeah.
So
you mean what in here? You mean this? Or?
Yeah, so the simulation is finished. So you have like 2 seconds, right?
Yeah. Yeah, 2 seconds at all, 1 second in the hot loop.
Right. So now there's an output, right? You should have some kind of be able to get some visualization.
Oh, I haven't written any output. I haven't set.
Oh,
you can say it at one time on the terminal. Since I have compiled this OpenPMD, I could write now OpenPMD files you can analyze.
Oh.
I'm not able to do it. It's so much work. No. I was running now only. I only consume now energy and store everything. But yeah, in general, you could now also write output. One thing also Micha already mentioned is Isaac is for regular grids and visualization framework. You can add to your simulation. You need to write some adapters that Isaac can handle your data. So because it is really without copying using your data representation, you get some index information from Isaac. You need to translate it to whatever hierarchy your data has. You don't need to provide the value back. You need to say if it is a scalar value or if it is an array or vector of n values and so on. This is then used. You can do glowing gas simulations. You can visualize particles and isosurfaces. It's an alpaca. Isaac should not replace, for example, a ParaView or other really complex tools where you can also run your Python stuff to change your attributes and everything. It is really an easy steering tool that you can see during the execution of your application what's going on, because very often other of you also said it, you see already in images a flow that something is maybe wrong or not behaves like expected. For example, you with your simulation, if you see everywhere the magnetic field or so, then something is maybe happened. So you can detect it on large runs, for example, on Frontier during the simulation is running. It is a little bit hard because this also means you need to be at your PC at the moment where the job is running. Since we have batch systems, you never know when the job is running. Sloan is giving you an estimation, and most likely you stay up in the night. Then the system is saying, oh no, I shift the job 2 hours in the future. Then yeah, you are lost. So it's a little bit hard to use in current batch systems, this workflow. But for example, on our own system or on other systems, we get sometimes allocations where we really know now any of our jobs is going straight forward to the system. It is starting instantly. Then you can use it. Very short overview. This is Isaac at the end is running in your browser. The interface is really a prototyping interface. You see here Also, the data sources is a little bit like what you have in OpenPMD. It is another way to say what is the data source. It is then, if you add more data sources at compile time to Isaac is compile time, you need to compile it into your code. You have the different stuff, and here you have an function, for example, you can add that you can define what is the property here. The value is used, the length out of the small vector is created, then a magic factor is applied, and you can then give it different range in your simulation. You can define color bars and the gradients in the color bar, and at the end it's visualized. At the moment, we do not have in our protocol how everything is communicated to the client. You can also have multi-client. So if I would start an Isaac simulation now, everyone in the room can control it if you have access to the system in your web browser. It's quite fun if 5 people try to rotate the same simulation. What currently missing in Isaac is something like, what quantity do I see? What is color yellow or something like that? So it is a vision, and like I said, it since over 10 years now, to go into interactive HPC, that you maybe can use this streaming tool, or is not PowerView again, but you see, oh, something here is maybe interesting, that you have a way now to mark the region which is interesting, and then say, okay, send the data of this region, communicated back to the simulation, send this data of this region to my Jupyter notebook via streaming with OpenPMD, for example, and then you can do, at the same moment where you do the live visualization, do real analysis of your data in your Jupyter notebook, for example.
Is this rendering done on the HPC nodes, like it's streaming the pixel data PNGs to your browser now, or is this streaming simulation data and your browser is running this WebGL? Like...
No, this is really a software renderer. This is running on each of the compute nodes, side by side with the simulation, using the simulation data, producing, everyone is producing a part of the picture. It's composed with IS3. Is creating an image, and this one, so it is image, or as Scream send it out, or there was a plugin also to send it to YouTube for your 3D head glasses, then going somewhere to your consumer where you like to watch to the image. So the data transferred is then not as big, it depends on the resolution. So if you are sitting here in Germany and you are on front, you should not use 4K because it's a little bit ugly, but a full HD image is easy to transfer.
So if you're like clicking and dragging with your mouse, you're just sending your mouse movement to the running job also?
Yes, so there's a loose-defined protocol behind, so each action is then sent to everyone, and each compute node is applying the camera cam rotation and everything. Here you see, for example, MPI domains of this run, so colored, so you can also use it as debugging tool. In your case, it would be more impressive because you have much more colors, so you have load balancing and so on. So it's a visionary tool, not fully ready for real science at the moment. So, but for nice presentations.
It does not block the simulation, so there's no overhead of the formula simulation itself, but does it somehow block for data?
The rendering of the image is you can say the blocking. So it is. Here we have, for example, the time. I don't know, is it somewhere how many nodes it was? Here's one example how long the render time is. So, and the rendering is going on the GPU side by side with your simulation. So as long as the render kernel is running, or we have multiple render kernel, as long as the software renderer is running, your simulation cannot run. So because also the data should not change, so it would be not good if since we are using the data directly, it would not good if they get updated and you have nice artifacts in. It really depends also on the resolution, and it depends also on the number of compute units you are using. For example, here you have how long Average time step. Yeah, you have here how long the simulation took. Red, blue is how long the visualization, the render kernel take. And if you use more GPUs, the rendering overhead will go down because less portion of your volume data will be steered in the final image. So except you go with camera directly to one of the edges where one GPU is doing everything. But this was a plot before where we run a simulation, added somewhere the camera, and automatically was going over all direct dimensions of the simulation and rotated the camera. And it also depends then on from where you are looking, how fast your software render is. Since we are reusing the data structure of the user, it could be that the memory access from one side is not as performant as from the other side, because sometimes you go really the line memory, so the data loading is quite fast, and sometimes you maybe use the worst way to iterate over your data, then it is fluctuating. But it's absolutely depending on how many sources you activated and your resolution, and yeah, that's.
But actually, so saying from with NVIDIA, I think this is the summit slide we had before, principle rate takes more or less half of the runtime, goes into utilization, and even only for the very large runs, it's perhaps only a quarter. So this would mean there's nothing you run for each run. It's only for some selected runs where you see, okay, now perhaps something will happen. There's nothing you have always run with it and monitor your run.
I think the question is now, I think Richard did this, no, Felix did this slide. The question is also how large was the simulation. I assume this was something like 20 frames per second. So in that case, yeah, you end up with, here we have an total time of rendering, for example, is it milliseconds? Yeah, make it milliseconds for one step, the different steps of the renderer. And you need around, for example, on AMD GPUs, 100 milliseconds for rendering of, I think it's full HD image with this volume. This is quite small. So the simulation will have, the overhead will be really large compared to simulation. And yes, maybe you do not like to run with each simulation, but what also would be possible, okay, do not render each of the frames, maybe you render only each 100 and stream the output directly on your web page of the institute or something like that. And then you have a list of all simulations running on your cluster, and you can get a snapshot from time to time. Also a very nice advertisement. But then you need to build up the full workflow to have it on the web page.
Question.
Yeah, I'm ready.
No, I'm quite interested. One said that you would like to utilize your underutilized CPUs while running GPUs with ISAC, so that this overlap when you render and when you compute will be somehow asynchronous.
Pico GPU do not support it, but in general, Isaac is accelerated by Alpaca. You can, so if you write a native Alpaca application, so Pico GPU has a coupler under the hood. So coupler is like CUDA and is defining you are only allowed to use one accelerator of Alpaca. Select one, and that's all. So I cannot run easily Alpaca accelerated code on CPU and GPU. But assume you wrote your application from scratch, use Alpaca, then it's quite easy to say, okay, my data will be all data I like to visualize will be put it on the CPU double buffer from the GPU. Your simulation is going on the GPU, and you use the CPU to render your data. It sounds a little bit crazy because normally you use a GPU to visualize stuff, but yeah, Alpaca allows you also you can say which accelerator you like to use. You can also accelerate your visualization since it's a software renderer, independent of OpenGL or Vulkan or something else. You can run it on CPU. It will be for sure slower than on GPU because the CPU is not as performant. But it's a possibility. You can also do it as vice versa. So run take your simulation. BIT1, for example, and visualize it on the GPU. It's also possible. So, okay, I think Isaac Michael also talked already about it. We have one tool, for example, the CUDA MEM test. This is what we execute before of any of our simulation of Pickon GPU on each cluster, on each node, on each GPU to check if the GPU can be used. So can I grab me from my MPA rank and GPU and we perform some yield tests. This is, for example, a project we forked from someone else. It was in the past on SourceForge. Maybe the older of you knows SourceForge. Now you get spammed with this ugly advertisement and so on if you join this site. Since it was not developed anymore, about 10 years ago, we took over the software in our repository. I think it give also a notification to the original author that we now maintain it now, added some new features. For example, you can use memory in CUDA, for example, that you can use CPU memory directly from the GPU. Something like managed memory. It was the first version of managed memory, you can say. It was a little bit more explicit. And I added, for example, the feature that you can test if this memory feature is really working. So you can test from the GPU your CPU memory. You can fill it with everything and read it back. And it was helping us once in the past because the NVIDIA driver had an issue only in a typical university. I don't know why, with the K80, that this feature was totally broken. Yeah, we maintain it. This software is quite nice. It's quite easy, the implementation, and we took it over, we maintained it, and now I had in the last time a few issues about it, and very nice project. So yeah, look left and right for already existing solution. Maybe you only need to tweak a few lines, and then it's exactly the tool you need.
I looked in your example script, a job script for example, you only seemingly using CUDA MEM test to test the nodes. Are you also doing some sort of testing whether nodes can reach each other and messages work?
Before CUDA MEM test, there is a very tiny application running which is checking which local rank ID we have, that we can say, okay, you need to use the first GPU and use the second and so on. This is testing MPI, but only grabbing the rank, because MPI do not have, I don't know why, a function to say what is my local rank ID. You have it in environment variable for Slurm, but they already differ by naming, so there's no generic solution. So we wrote a small tool what is doing the same. We're doing a pick on GPU, and this is our MPI test. It would be better to test more if MPI GPU direct, for example, is working end. But normally it is not our task. This is something the facility should provide to us. That we have CUDA MEM test, maintain it, use it, is more than less a workaround from the past, and we are happy very often still to have this tool.
We have a short example on how to use Alpaca, just to get a feeling how this looks in code. For example, for Cocos, we have loop structures that they're using. Just want to have a comparison how it looks.
Yes.
Well, other GPU, like
we support this. Right. I'm now grabbing slides from Jan Stefan. Oh, I'm in Lama slide, I think. Wait.
There was an Axpier.
Yeah, it was Axpier. Ah, this is a general overview. Okay, Alpaca is supporting serial execution, OpenMP2 execution, OpenMP5 we stored away, OpenSSC we stored away. We're supporting Circle, so you can go with Circle to NVIDIA GPUs, to AMD GPUs, to CPU, and all Circle is supporting FPGAs. And we have HIP support, so you can natively use the interface AMD is giving to use AMD GPUs. So you are free to use any of these ways to talk to your device. Yeah, this is currently showing our ecosystem, and I like to switch to the one basic example. Yes, the AXP example. We have also examples in Alpaca. So if you are familiar with CUDA, in CUDA you would remove this struct around. Instead of operator, you would write underscore underscore global underscore underscore, and this is normally an entry function via in the C++ world. So in Alpaca, you need to pass in a functor with your kernel.
Can this be a number?
It can be a lambda. Yeah, but the only thing is this is all the arguments the user like to have in this kernel, and this argument, the accelerator, you get always for free. You need to have it because this is our way how we find out what we need to do. Are we on a NVIDIA GPU, on HIP, or where are you? This is some context. So this object is. It depends the complexity on which accelerator it is. You have two ways to write an abstraction layer for your application. One way is the typical way you would write if define. Then there are for each compiler some predefined NVCC compiler. Okay, now I know that I have CUDA or if define CUDA. Do something like that for a memcopy. For OpenMP, I do something else, and you have a lot of if defines in your code. This is something we try to avoid. Therefore, we have really a C++ object, so that the user do not need to fiddle around with 1,000 if defines, where the full complexity of the accelerator is in. So this object contains all the math functions we are supporting. What is the definition of the math function? We support sometimes more math functions than the C++ standard is giving you. How to map it then to the native implementation of the vendor and. So this is a context you need to center around always. If you call somewhere in the code a sign function or or you like to use a random number generator, you need this accelerator. You need it very often, and you see it here, for example. Okay, what is my grid index? It's what is my grid? Well, no, what is my sweat index within the grid? So you have hierarchies here. So Michael showed. It's not in this presentation. Michael showed an image that we derive the hierarchies from CUDA. We have grids, blocks, sweats, and we have an layer element level. No, you can't forget about the element level. It is here. We have the element level, and it's here one dimensional. So we say, okay, what is my index of the sweat within the grid? Here, work division.
So that's a combination of the grid index and the block index.
Yes.
The track index, the block index from
Exactly. So this is what you also typically do in NVIDIA in the beginning. You calculate at the end an unique index for the work of your sweat. Yeah, then guards that you do not access the memory out of the range, and then we apply it here to n values because we have an element layer here. You can configure from on the host side during the start that you like to have. You like to operate on more than one value per element, going something into the direction of the dynamic vector length. So, but in Alpaca, you need to handle the element layer by yourself. This for loop, for example. So this would be the simple XP on a GPU, and on the GPU it is a little bit more code, but it is Alpaca is very explicit. You need to say really everything. This starts okay, how many dimensions kernel indice will have later on. So we run XP, we only need one dimension. CUDA, everything is always three-dimensional. So you have always X, Y, Z component. But here in Alpaca, you can really say, oh no, I don't know Y and Z. So I like to solve a one-dimensional problem. What is the type of the indices? Because it is a different, so by default, CUDA will give you all indices if you ask for the block index on a 64-bit architecture, you will get a size T or a 64-bit type. But Alpaca allows you also to say, oh no, I will handle all my indices as integer, because again, this means we save one register per property we store. If we store our thread height index or our grid index, we save one register. This is amazing and very important if you are then in the phase where you really tweak for the last piece of performance. Then you define an accelerator. An accelerator is a mapping to the device. So okay, there's a name CUDA GPU, CUDA runtime. You say how many dimension it is, what is the index type. Then you grab a host device, and host device you need it, for example, to create the host memory or something. You also create a device with what you define, the CUDA device. You need to say you need to create a queue, same like in CUDA, or this is stream in CUDA, for example. You need to say this is one policy where you can say, should the queue behave as asynchronous queue, or should it be blocking? Blocking means if you apply a memcopy or a kernel into the queue, you do not get back the handle into your application until the operation is fully performed. In an asynchronous queue, you only say, okay, run a memcopy, and you are responsible as next time when you use it that this operation is ready. So you need to ask your queue, is this operation ready? Are you empty? Or you need to enqueue an event behind. So it's the same as in CUDA. So it is you need to call event record. You can ask the event later on, is my operation or all operations before in this stream ready? In that case, it's queue. Yeah, you need to define it. It's quite easy as blocking. We do not need to synchronize. Therefore, after the memcopy later on, you define the extents of your vector. You create an buffer on the host. So it is in a CUDA example, it is always this, where you use malloc or new or something like that. You create a buffer on the device, same size, so same extents. You do a memcopy with it. You do a memcopy from this buffer to the host buffer, no other from the host to this buffer with this extent. So you do not need to copy everything. I think the extent you can also skip if you copy the full buffer. The work division is your configuration, what you normally wrote, how many blocks I need, how many threads each block has. So we have a helper tool. You say which accelerator you like to perform your problem. You say how large is the problem. You give also a device in, and I don't know this value at the moment. There are some more values, optional values, where you can say should my block, if you run an n-dimensional problem, should my block be cubic, or is it allowed to have any shape? And then this is a small helper which will derive you a good configuration to run your kernel to solve your problem. It is not necessarily the best, but it's a good, easy entry to start. So then you say, okay, and queue into the queue is a kernel we defined before. After the kernel, since we are blocking, we do not need to synchronize again. Else we would synchronize the queue before, like in CUDA. Else you copy the data back, and you can verify if everything is working. Yeah, here again, this is what we are currently supporting as well. This was a tiny kernel of Alpaca, how to write it. This is very, very similar, but on the host side, you have a lot of more definitions, because you need to define what is your mapping and everything. So, and later on, you reuse it. So you grab once your device, and then inside of the code, you have an instance of the device, and this will be used many, many times. Not as in CUDA. In CUDA, you always say, set device and you give the index, and this is not really handle the instances. So you get an instance of a device back, you get an instance of memory back, and you need to then give it to your functions. Down. Yeah, so a new feature in Alpaca, so we will have soon a new release. We will have the 1.0 release. This means nothing, but we decided to have a 1.0 release. You can use Alpaca within Godbolt. So we have on the Alpaca. Okay, as always on the top right, we have the docs link. And here we have also, if you put this into Godbolt, then you need to pass this ugly name I showed you from Pick on GPU before into the Godbolt compiler string. Then you can play around with Alpaca within Godbolt, analyze your code, see what vector instruction may be on a CPU coming out, and quite nice feature to explore many examples or test a little bit the behavior.
Oh, that works like what? Pulls from this local, then this include together.
Oh, this is the compiler explorer is a website where you can. Oh, there's an example. Is it my? Oh, it's my example. I thought we had an example behind. Would be good idea. You can write any C++ code. You can select your compiler. You can then say what you like to see. You can see the assembler code, and you can pass here different kind of. Oh, no, this is a real example. Oh, that's cool. Here, for example, he was then compiling it with C++ 20, and then it is executed directly somewhere in the cloud. And this is running Alpaca in the cloud. It was CPU serial execution, so one core. So, and there are a lot of examples. Yeah.
Just a parenthesis. We do have also for the API compiler. The same, yes. So we have our self-hosted, how's it called, the compiler store.
Okay.
And we added our compiler so that you can see when you type some of your source code, you see the. I didn't know that you were used to, so that would be useful. Otherwise, I could have shown you. We have it. So we have the support with our compiler.
That's cool. So for what you did, this is tiny example is quite useful.
Yeah.
For a big application like on GPU, I do not suggest it, and I don't think it's possible. Yeah. Some questions to Alpaca?
You're tired for today, they are not using.
If not, I would say 2 words to some other project and not go into the details of it, if it's possible. Yeah, very short. We have a project which is you can already use. We currently not use in GPU. We like to use it, and this is motivated maybe also what Plasma-PEPSC is doing. Your simulation is not only running one for loop. It's many tasks or kernels. And then also you have communication, because which is tasks again. And you need to fiddle around with all the dependencies. Which task is using what? And can I run this task in parallel to another task? So a lot of libraries out, HPX, like yesterday we heard the task library. StarPU, yeah, StarPU and so on, where you can define dependencies between tasks. But what you need to do as user, you need to say, okay, I have a task and this task depends on this task. You really need to know, okay, what are the properties. So it is quite easy to make it wrong that you say, okay, that you miss a dependency. And so we developed red scripts where you define resources. The resource can be anything. So in the easiest way to think is a buffer. And you can define access modes. So you can define what is a read, what is a write, for example, and how is the read stay in comparison to the write. Can I execute a read in parallel to a write? No, I can't, because the write will change my data. But if I have an atomic operation, I can also define an access mode atomic. In atomic add, for example, I can run two tasks with atomic add to the same resource in parallel, because it do not matter in which order it will be executed. And I can define also my own access modes, and I can define domains within a resource. So a simple 2D buffer, I can define, oh, I now like to perform an add operation on the top left only, and someone else is, and the right, for example, and someone else is saying, I like to define a task which is doing a write on the corner left. They don't overlap both of the domains. So this means this one can run in parallel. So you only say which access, which resource you need for your task, what access you like to have, and then you simply say, okay, start the task, and you have normal, like we call it in functions. So here we have on our README a very small example. You define a resource A. He is saying directly and place a task. He is placing another task. He's saying write to A. Here read and here read. This means at the end the task graph will be generated during the runtime. So you can also put it in a loop, and in each loop also decide to skip a task. So it's no problem if you say I have if in between, for example, think about this task is IO. So you can put a loop, an if condition around where you say, okay, IO, I only like to perform each fifth step, for example. And then the task graph looks always different in each iteration. And also do not assume that after one iteration you need to block. Why would you like to block the simulation after an iteration? It can still run everything in parallel. This is what I said in Pick on GPU. The left top of our simulation can be another time set the left button, for example. And you have a way to place tasks, describe tasks in a very elegant way in C++. So lambdas or functors again. It is extensible that you can handle CUDA. Other libraries, you can use Alpaca. You can also add MPI to it. So even if MPI sometimes has a restriction, oh, I have no threaded MPI, all my MPI commands must be executed from the same thread. This is possible to describe with red clips, and red clips will take care then about the dependency graph. So it knows about the resources, it knows about the access, it knows about the domains where each resource will be accessed, and then it knows about all tasks which are currently in queue. So if you can think about you run your code until here, it knows only this world. If this is coming again, then the graph will be extended. Then it is going through a scheduling transformation step, and then it will be executed as soon as possible. And with that, we like to substitute our prototype of the event system in Pick on GPU, which is now 15 years old, the state machines, because we cannot really say, okay, now we do an MPI, and this MPI operation needs this resource and this, and then the IO maybe is, or we call it plugins, for example, for doing small histograms on the fly, or Isaac in between. It is quite hard then to say to which task we depend. So this is automatically derived, and you hopefully run everything in parallel what you can run in parallel. So this is a very nice library. If you are at the point where you are faced with many tasks, you should have a look into it. And it is not what you said, or one of you said on Monday, with StarPU, that you see some global area and it is solving your Pegas stuff. It is not handling errors. You are responsible for your data. It is only describing access mode and is saying you, okay, now this task can run and this task will be executed on whatever you say. You can say on the CPU, or the task is calling a GPU function also. So it's only for one node, but you can use MPI and also handle your asynchronous MPI. Alpaca has an own organization. You saw maybe before. Beacon GPU is in our group repository. I also like to make you aware. It is a very good practice maybe for projects to start a new organization on GitHub, for example, and put the project in that is not branded with your institute or something like that, because this could be a showstopper for the community to use your code or to extend your code, not to use your code, but to extend your code. And for Beacon GPU, we haven't done it for now, but for Alpaca, it was located also in our repository. I was years ago then putting it out, giving it an own organization, and we handled it now without brandings in the documentation. We describe everyone who's participating through the project. We acknowledge also each developer. If you push one pull request, you are in the next release on the author list. We have a full ecosystem here also, and Malloc-MC, what I like to mention. So if you need fast allocation on GPU at some time for a pre-allocated heap, then have a look into Malloc-MC. This is simply a new on the GPU, we can say. Also, CUDA provided and AMD provided a HIP, but the implementations there are really slow compared to Malloc-MC, because they are not made that each thread can allocate a small chunk of memory. So this is a chunk allocator which is explicitly written that it can is fast on a many core architecture. So this is also a project we derived from the University of Graz. So I found it on the website. It was really amazing. I fixed a lot of bugs. Then we extended it, and now it is living in our repository since many years. So there are a lot of more projects I don't like to talk. Llama was mentioned by Michael also about the memory abstraction. Really cool, I think this is also something where mostly someone is interested who really likes to tweak the last piece of performance, get a better overview about your memory pattern. But if you start a new project, it does not hurt to look into this project. It has millions of examples. It also provides you ways how to explicitly write SIMD instructions. So it has support for XSIMD and for the upcoming GCC SIMD extension. You can select which one you like to use, and you can formulate explicitly, this is now SIMD, and then it is not, you do not rely on auto-actualization of your compiler. You really say, okay, you run now this command as SIMD command. So because this SIMD standard, what is coming with C++, has for different architectures real SIMD commands. And yes, there are different implementation, and Llama is also implementation agnostic. So it does not matter if you use XSIMD or if you use the GNU SIMD prototype, or if you have your own SIMD library, you can also write a small adapters that Llama can then handle this SIMD extensions. So I think that's all that's late. Thank you for your attention.
So we are really late, tired, I must say. I still have some presentation needed for tomorrow.
I think